It is my pleasure to introduce the first talk of today by Fontaine, who will talk about real forms of complexified Hamiltonian systems. And her colleague, Philip Arathon, will join her in the parallel session later on today.
Okay, yeah. Thank you very much for organizing this conference. It's very well organized. I'm going to presentation, so it's gonna do the parallel session, and let me a bit explain what we would like to do with it in the title. So we don't really complexify manifold in this talk. We will go the other way. But if you start with, for example, a real Hamiltonian system, let's say just R2, and you take a Hamiltonian function, which is like, just say polynomial, then it's easy to complexify everything. So you go on C2, you have a holomorphic symplectic form, and your Hamiltonian, you take all the complex variables, it becomes complex, and you get a holomorphic Hamiltonian system. And what we wanted to demonstrate in that work is that from a holomorphic system, which is a rigid one, you can obtain different real forms, like different real Hamiltonian system that are all like sort of the same, they're all related by this holomorphic system. So let's try, oh, I cannot change my slide. Okay, that's fine. Yeah, so I will start with this example. You are on C2 and you take complex variables and you have a holomorphic symplectic form. Now you take just a random Hamiltonian, like complex. And we would like to obtain a dynamical system on a real form. So a real form is a totally real submanifold, which of half dimensions. So it's C2, it will be a copy of R2. But now there are several copies of R2 in C2. And we would like one on which the Hamiltonian is real. You can have different one. Like one example is you just said the imaginary parts to be 0, and then the real form is R2. The homomorphic symplectic form restrict to a nice canonical real symplectic form. Or you can take another copy of R2, and you also have the restriction, which is a real symplectic form. Now what happened with the Hamiltonian? It does. Okay, so when you restrict this Hamiltonian to both real forms, you obtain a real function. So altogether, you obtain two real Hamiltonian systems. And if you have the Hamiltonian, you can get the Hamiltonian vector fields. And in that case, because it's two-dimensional, the flow lines, if you forget about parametrization, the flow lines are just a level set. So you already observed that you have different dynamical system on different real form. And this is what we would like to show in that talk, but we would like to be a bit more general about it. Like we will take a holomorphic symplectic manifold that we fix, and we try to obtain have a theory that tells you how to obtain a real dynamical system on a symplectic real form. So as I said, we are not really doing complexification of the object. We already suppose that we have a homomorphic manifold which is fixed, and we try to obtain real system out of it. So there are two parts of that work. Like one part has to do with dynamics. So homomorphic Hamiltonian system, how do you get real one? And what happens if you have an integrable system? And on the other hand, there's also a geometric part which shows you how you can define real forms, like for Poisson geometry. What happens if you have a group action on it and you want to know how does the whole thing behave under Poisson reduction? And so Phil is gonna talk about that part, and I'm gonna focus on the dynamic part. And there's also a part of the work that has to do with hyperkähler geometry, and this is actually used, you will see, to find an example that we will call a compatriot form for the spherical pendulum. So the spherical pendulum is a real Hamiltonian system, which is defined of a cotangent bundle of a sphere. And in fact, we will see that S2 cross S2 can be seen as another real form of the same holomorphic system. And we will see what the spherical pendulum is on that form. So the first definition is what is a real form. So you take a holomorphic symplectic manifold and it has a complex structure I. Because the form is holomorphic, you can write it into its real and imaginary parts. And then you can check that as a real manifold, M is symplectic with respect to both. And those two are not arbitrary, they are related through the Cauchy-Riemann equation. So a real form of a complex manifold is a totally real submanifold, which has dimension. So it means that you can split the tangent space in that way at each x. And so this is just a real form. Now, if you want this real form to be symplectic, we will call it real symplectic if when you restrict your homomorphic form to it, this is purely real. And on the other hand, you can also define an imaginary symplectic form. When you restrict the homomorphic form to it, you get something purely imaginary. You can treat like both in the same way. I will mainly talk about the first one, but everything works really similarly if you take imaginary symplectic form. So if you take one such real symplectic form of M, then it is a Lagrangian submanifold of M with respect to the imaginary symplectic form. And as a consequence, so because if it's purely real, it means that omega I will be 0 on n, and n is of half dimension, so it's Lagrangian. And if you have this, you can check that the real part restricted to n is non-degenerate as a consequence of the Cauchy-Riemann equation. Now, real forms can be obtained as fixed point set of real structure. So a real structure is a anti-holomorphic involution on M. So it's square to identity and it anti-commute with a complex structure. And in that case, a fixed point set is a real form. And if now you have a symplectic structure on M, then you can ask your involution to satisfy this to be symplectic, conjugate symplectic. So it's symplectic with respect to the real part and anti-symplectic with respect to the imaginary part. And same thing for the imaginary symplectic structure. And in that case, the fixed point set are real symplectic and imaginary symplectic form, respectively. And let me show you some example. So the complex sphere, it's same as the real sphere. You just take complex variables instead of real. And this is a complex, it is a complex manifold and it has a holomorphic symplectic form, big omega. And on it, you take like the three involution that are anti-holomorphic, and you take the fixed point set, you will get the sphere, the two-sheeted hyperboloid and the one-sheeted hyperboloid. And in fact, this sphere will be a real symplectic form and as well the two-sheeted hyperboloid, and this one is imaginary symplectic. And Phil will explain it's in this talk that in fact those involution come from Lie algebra involution, because CS2 is also a coadjuvant orbit of SL2C. And on SL2C, you have a group involution, and one of them is the fixed point set. One of the fixed point set is a compact real form, which is SU2. And this is why here you get a sphere, which is also a coadjuvant orbit of SU2. And here you will get SU11 and here SL2R. Another example, if we want to talk about dynamics, these are cotangent bundles. So the cotangent bundle of a complex manifold is also a complex manifold. It's symplectic with canonical symplectic form. And if you take a real structure on C, so you can lift it on the cotangent bundle such that it becomes a real symplectic structure. So the lift is defined like in a real way, but it has to be anti-holomorphic. So you take the conjugate here, and you can choose signs. And depending which sign you choose, the fixed point set that I wrote here is a real symplectic form of the cotangent bundle. And you can identify it with the cotangent bundle of the fixed point set of little r. So this is a way to obtain real phase spaces in complex phase spaces. So we are interested, how does that behave with respect to dynamics? If you take a Hamiltonian, which is holomorphic, there's no surprise, it works the same way as in the real case. You can define a holomorphic Hamiltonian vector field. And oh yeah. And how can we, what will we talk, what would we call a real form of a holomorphic Hamiltonian system? Well, for the phase space, you will take a symplectic real form, n, and the restriction is purely real. And for the dynamics, you would like the flow of this holomorphic Hamiltonian vector field to leave that real form n invariant. So on the real form, the flow, it means that the flow of the Hamiltonian vector field is the same as the flow generated by its real part, only on that real form. And it's a reasonable assumption to have, and we can show that this happens if the imaginary part of the Hamiltonian is locally constant on n. So in particular, the Hamiltonian doesn't have to be purely real. And so the real form will be this symplectic real form and the restriction of the real part of the Hamiltonian to n. As an example, you can take the complex 2 sphere, and it has a cotangent bundle. And you take the real structure we've seen before, and the fixed point set here gives the sphere and the two sheeted hyperboloid. And if you want real structure on the cotangent bundle, you lift them with a plus sign so that you get as fixed point set the real cotangent bundle on the sphere, and well, just one sheet of the hyperboloids, and both of them are symplectic real form. And now, if you take just the free Hamiltonian, then it becomes purely real on both. So in particular, the flow of the vector field will leave those two real forms invariant. Actually, there's nothing special about this free Hamiltonian. You could take, there are many Hamiltonian in general that satisfy this, like that are real on those two real forms. So you can somehow relate dynamics on spheres and hyperboloids in that way. And what happens if we now suppose that we are working with integrable system? So how do we define a holomorphic integrable system? Well, exactly, we define it the same way as for a real system. It's a collection of n holomorphic function on M that Poisson commute for the holomorphic Poisson bracket, and which are like, whose differential are linearly independent almost everywhere on M. In the real case, a real integrable system is exactly the same. You just replace the Fi will be like smooth function. Here it will be Rn. Yeah. Oh. Yeah. So, and when you have a holomorphic system, usually we think of F1 as being the Hamiltonian H, and the other Fi's are the integrals. So these are like quantities that are constant along the motion of F. So sometimes we call F1 the Hamiltonian, and the other one are like first integrals of H. And how can we define a real form for holomorphic integrable system, well, you can expect that you will say, as before, that the Hamiltonian, the first one, will leave some symplectic real form invariant. But it will be maybe a too strong assumption to ask that all the other integrals preserve that real form. So it's quite reasonable to ask just F1 leaves a real form invariant. And that's what we have here, that you have a holomorphic symplectic manifold, you take a real phase space in it, or real form symplectic, and H leaves it invariant, then you can say that the restriction of H to N is real, or at least imaginary part is constant, is a completely integrable system, which means that it has additional integrals of motion, which are in involution and independent almost everywhere. So how does that work? Well, if you take all the real parts and the imaginary parts of the Fi, and so there are real function on M, you restrict them to the real form, and all together with the Poisson brackets, the real Poisson brackets, they generate an algebra which is called closed under that bracket. And you can show that this algebra is actually complete. So complete, it means that if you take any function in that algebra, you take the Hamiltonian vector field, all of them will generate a subspace at some point. You evaluated at some point, they will generate a subspace of Tn, and you take a point such that this subspace is of maximal dimension. And if this is co-isotropic, then the algebra is called complete. And it was shown that by Bolsinov and Jovanovic that if this complete algebra is moreover an algebra of first integral of H, then the system is completely integrable. So when so here we just have a complete algebra, we show that it's a complete algebra. But if you suppose that H leaves a real form invariant, it means that all the other imaginary part and real parts, because they commute, because the Poisson commute, they are all constant along the flow of H. So in particular, the algebra that you get in that case is an algebra of first integral. So that gives you complete integrability. On the other hand, we can also say we start with a real symplectic form and we have a real Hamiltonian system on it, with analytic integrals. So if you have analytic integrals, you can take the holomorphic extension in a neighborhood of the real form. And this also define a holomorphic integrable system. And so that's a bit the idea we wanted to illustrate, that if you start with a holomorphic symplectic manifold and you take two different real forms, then suppose that on a system, you have a real integrable system. You have a real integrable system with analytic integral. Then you can extend it to a holomorphic system, at least in a neighborhood of the real form in N. And if this other real form is also included in that neighborhood, then you can obtain, you can construct another integrable system on this real form. And that's what we wanted to do with a classical example of integrable system, the spherical pendulum on the cotangent bundle of sphere. So you have H has kinetic energy here and linear potential, and it is invariant by S1 rotation. So you have an additional integral, which is angular momentum. And G and H are Poisson commute, and they are linearly independent almost everywhere. So you have an integrable system. And the image is called the bifurcation diagram, which is drawn here in the GH plane. The boundary here are the image, or are the image of the rank 1 critical point, so the relative equilibria in that case. And the dots here are the image of the rank 0 critical point. So we start with now the complex manifold. You take a product of two complex here.
Marine, it's a 5-minute warning.
Yeah, it's finished almost.
Okay.
Yeah. So here, if we start with a homomorphic manifold, which is a product of two complex spheres, both of them have homomorphic symplectic form. And there's one real form, which is quite straightforward. It's like a product of two real spheres, with the restriction of the homomorphic form is the symplectic form on this product, the standard one. And this is a real symplectic form. But there's another one which appears to be a cotangent bundle of S2 with canonical symplectic form. And this real form is actually imaginary symplectic. And this is where the whole hyperkähler geometry is coming into play. And that's why Phil is gonna talk about later. So we can take this spherical pendulum on this imaginary real form. We can complexify it to get a holomorphic system on this complex manifold. And we take it, we push back on this other real form, and it turns out that the Hamiltonian is purely real. So you have a new real integrable system on S2 cross S2. And so what is this system? So I'll give you the Hamiltonian. What you see, this part comes from the kinetic energy of the spherical pendulum. And this is what the potential is becoming. And the additional integral, it's on TS2, it was like given by the SO2 rotation, also becomes an SO2 rotation on the product of two spheres. And the image of this, the bifurcation diagram of this integrable system is looks like a teardrop, and it has like 4 rank 0 critical values. And this is because when this system has only 2 rank 0 critical points. But when you complexify, when you have a complex Hamiltonian system, this one also has singularities. And actually it has 4. And when you take these 4 critical points descend on that real form, but they do not go on this real form. No, only 2 of them belongs to the T star S2 real form. So this we can think about this system on S2 cross S2 as being a compact real form of the spherical pendulum, a bit in the same way that we will talk about compact real form for Lie group. And yeah, so that's the end. I think I will stop here. That's time. Thank you.
Okay, thank you very much, Marine, for this wonderful talk. So let's all give a round of applause to Marine, including emojis. Let's all give an emoji round of applause to Marine. Thank you very much.